guys. So just firstly, if thanks for the organizers for the invitation. It's nice to stumble across this seminar series. And if anybody has questions, just hop in at any point on the slides. So don't, wait to the end if you've got questions on any of the specific stuff that I'm going to talk about. So as the title suggests, I'm going to talk about perturbation theory at finite temperature. I'll just briefly sketch some of the known inconsistencies or the known problems of perturbation theory, where they come from, and an idea of their potential resolution. And that's the kind of focus of this recent paper. And there's a kind of common theme that runs through all of this, and that's this notion of thermoparticles. So hopefully, if people take anything from this seminar, it's just to understand what this notion of thermoparticles are, and the different contexts that it can be applied in. So this is the kind of the seam that runs through the whole of this this talk and the various different analyses that we've done. So yeah, so as I said, I'll talk about perturbation theory. So I'll just give I'm sure many of you here study perturbation theory or use perturbation theory on a day-to-day basis. What I'll do is I'll just just give a one-slide sketch of this at finite temperature, and then just discuss the subtleties. So what happens when you switch on a temperature, what sort of issues arise here. And then what I'll do is I'll talk about looking at or studying theories on the lattice at finite temperature and comparing the results that you get from lattice simulations to perturbative predictions, and see if you get deviations and trying to figure out where they come from. And this leads into this notion of thermoparticles and then thermoparticle perturbation theory. Okay, so I won't labor the point here because I'm sure most of you, or if not all of you, know perturbation theory at finite temperature. But just I wanted to sketch the kind of, the two main approaches here, the real-time approach and the imaginary time approach. With the real-time approach, you calculate along the Schwinger-Keldysh contour. So that leads to this doubling of the number of fields. So the fields can be restricted to either the plus or the minus contour going forwards or backwards along the time direction. And this just leads to 4 different propagators that enter into your perturbative calculations. So you have more bookkeeping basically to do. You need to take into account all of the diagrams that come from this. And when you do this, you actually arrive at consistent results that agree with the imaginary time formalism. So in this approach, as the name suggests, you instead work in Euclidean spacetime. So in that case, with your Euclidean propagators, the energy is discretized. You do these calculations in Euclidean spacetime, and then at the end, you do an analytic continuation in order to recover your real-time results. And it just depends on the application that you do. Sometimes the real time's easier, sometimes the imaginary time's easier, but both of these approaches are equivalent to one another. Okay, so I think we all know that perturbation theory has problems at finite temperature. So one thing that's quite famous in QCD is you have this famous Linde problem, so that the perturbation theory suffers inconsistencies above a fixed loop order. And we also know that perturbative series has poor convergence, often need to reorganize the perturbative expansion, doing so infinite resummations or applying functional techniques. And basically both of these problems stem from the fact that as soon as you switch on a temperature in perturbation theory, you get components that you don't get at zero temperature in the vacuum theory. And these components are highly sensitive to the infrared dynamics. So if I take a classic example, this so-called cactus diagram in 5-4 theory, you can show that this has a subcomponent that looks like this. And what you find is that even after renormalization, this diverges in the massless limit. So for massless theories, you get infrared divergences even after renormalization, and these don't appear in the vacuum theory. So they're purely caused by introducing temperature into the game. And it's these infrared divergences that lead to resummations. So the idea is that these infinite set of diagrams you resum up in order to recover a finite result in the end. Okay, so I think one thing that I want to draw attention to, and possibly people already know about this, but for those of you who don't, I want to draw attention to this. Sometimes these features of finite temperature perturbation theory are actually seen as a purely perturbative issue of the theory, but actually they're a symptom of a more fundamental non-perturbative constraint. So this is a relation or a theorem that was derived in the early 80s, the Naunhofer-Reichardt-Turing theorem, NRT for short. And the idea here is that what the authors tried to do is they tried to create a scattering matrix at finite temperature by constructing states, in and out scattering states that have purely real dispersion relations. And if you do that at finite temperature, what you find is that the S matrix must be trivial. So that means that if you have quasi-particle scattering, you can only do that if you have no interactions in the system. So this is quite a surprising result, interesting result as well. So why is it? So this is certainly not true at zero temperature, because of course you scatter on-shell states with one another. That's how you do your perturbation theory. Why is that the case at finite temperature, that you can't have states with purely real dispersion relations? So the QFT reason is the KMS condition. So this is obviously the condition that you introduce at finite temperature, how you introduce temperature into the system, how you define thermal equilibrium. So down here, you just you impose this condition on the thermal correlation functions, or in imaginary time, it means that your correlation functions are periodic. And what you find is when you impose this condition, this actually gives rise to very different spectral constraints than in the vacuum theory. And one thing that's actually very interesting is that by virtue of this condition, this implies that you lose energy positivity. So you can have negative norm or negative energy, states in your system. And the physics of that is just basically when you have a thermal medium that has energy, you can extract energy from that medium, and that's like creating a whole state of negative energy. That's the idea. So what's the physics? So why can't you have these real dispersion relations for your scattering states? And the reason for that is that basically because thermal effects are everywhere, even at large times. So you always have to take these into account, also in the definition of your scattering states. And when you do that, what you find, and we'll discuss this later on in the slides, is that you find that your spectral functions that would be deltas before now become broadened because of the temperature. You get a width, and that leads to imaginary parts in the singularities of your propagators. So in a sense, the fact that you can't have purely real states with purely real dispersion is because you have temperature in the game, and temperature leads you to singularities that have an imaginary part. So this, of course, has huge implications or significant implications. And this noted here. If people haven't read it, I really recommend checking out this paper from Landsman from '88. And basically, it means that if NRT is to be believed, it means that you can't do perturbation theory with either free field propagators or quasi-particle propagators with a real pole. Because if you do that, then you're immediately confronted with this issue that the scattering matrix must be trivial in your theory. So what's interesting about this is that this is not restricted to infrared regimes. This is also true at low temperatures, and also true for non-vanishing for non-vanishing masses as well. So this is not restricted just to massless theories. This constraint. This is a very general constraint that comes from the fact that now you have this KMS condition in your system. So this will play a role later when we talk about how we try to resolve this. But I think it's nice to sketch this where perturbation theory comes from on a correlation function level. So obviously correlation functions are the basic objects of interest that we study in QFT. And what you can show, this famous Gell-Mann-Low relation, is the classic textbook equation. I think this was derived sometime in the early 50s, is that basically your fully interacting correlation functions can be written in terms of the correlation functions of your scattering fields. That's what these phi zeros are. And what you can show is that in a vacuum theory, the scattering fields or the scattering states are actually on shell, and they're free. And so what that means is it means that when you expand this out and you compute your various different diagrams, like this guy, for example, it means that all of the lines that appear in your diagrams are free field propagators. So this is important because it's telling you that the structure of the propagators that enter your expansion come from the properties of your scattering states in your theory. And because they're on-shell scattering states at zero temperature, that means that your propagators have this standard form. Okay, so now we switch on temperature. So what happens to this? Well, as you'd expect, the vacuum state gets replaced by a thermal trace, but in the standard relation, the fields don't change. So these stay free asymptotic fields here. But of course, this runs into the issue with this NRT theorem, because the NRT theorem tells you you can't have scattering states that have real dispersion relations, and these free fields do have real dispersion relations. So the question is, does this cause problems? Does this cause inconsistencies? Is this the reason why you run into these various different issues with perturbation theory at finite temperature? So a couple of years ago, my collaborator in Frankfurt, Ove Philipsen, and I, we thought that it might be an interesting exercise to actually test the predictions of standard perturbation theory against lattice data and look to see what happens when we increase the temperature. Do the predictions are they still going to be consistent with the lattice data? Do they deviate? How much by? So what we did is we studied phi-4 theory. And the idea about the strategy behind this comparison is what we did is we did lattice simulations, and then we compared this to the predictions of lattice perturbation theory. So for those of you that don't know this, there's this great review or book, I should say, by Montvey and Münster that discuss lattice QFT, and also there's some good chapters on lattice perturbation theory. And as the name suggests, basically what happens is your propagators become discretized. So A is the lattice spacing, and then in the continuum limit, A goes to 0. This recovers the standard Euclidean propagator, because here you work in Euclidean space-time. And then the idea, as in any lattice simulation, you simulate on a finite lattice, finite volume, finite temporal size, and then you specify your lattice action to define the dynamics in your theory. So the goal of this was basically to take lattice perturbation theory predictions, and the nice thing about doing lattice perturbation theory is that you can use exactly the same parameters as what you use in the lattice simulation. So the bare lattice mass and the bare coupling that you use here, you can also use in the perturbative loops. And also you do these calculations in a finite volume as well. So they both have the same finite volume effects, and they both use exactly the same lattice parameters. So you're really doing an apples comparison, as opposed to, say, if you compared lattice data to continuum perturbation theory calculations. So that's the nice thing about this approach. And for the purpose of the interest, what we do is we focus on these two correlators, the spatial and the temporal correlator. The spatial, basically, you sum on the lattice over the imaginary time in 2 spatial directions. And in the temporal correlator, you sum over 3 spatial directions, or in the continuum, you'd integrate in this case. These are the 2 correlators that we're interested in. And what we do, basically, is we compute the predictions of this guy using lattice perturbation theory, and we compare it to lattice simulation data. And we look to see what happens as we increase the temperature. So as many of you know, the lattice temperature is just defined, it's proportional to the inverse of the temporal lattice size. So if we go to larger and larger temporal lattices sizes, that corresponds to smaller and smaller temperatures. So what we can do is we can run these simulations at different temporal lattice sizes, and that simulates a system that has increasingly higher temperatures. So what we do is we compare, as I say, the predictions of lattice perturbation theory of the lattice data, and what we see is that we see that for very large temporal size lattices, which is very cold systems, we see that the perturbative prediction, which is this orange line, you can see here, this agrees well with the with the lattice data, which are these upper black points. And as soon as you increase the temperature significantly, you go to a temporal size of 2, which is significantly hotter lattice system, you find that your perturbative predictions deviate significantly away from the data, which are the lower black points here. So another way of seeing this is to look at the so-called screening mass. So what you can do is you can look at your spatial correlator, which basically has a purely exponential form on the lattice, and you can look at how the mass parameter depends on the temperature. And what you expect basically is that as the temperature of the system increases, your screening mass also increases. And this is what we see here with the black points. That's the lattice data. You see as n tau gets smaller, the temperature goes up, your screening mass also goes up. But when you do two-loop perturbative prediction, you find that it actually has the opposite behavior. So the screening mass goes down as a function of temperature, and this is what causing you to be driven further and further away from the lattice data. Okay, so what's the source?
Sorry,
Can I?
can I ask?
Yeah,
Okay,
sure,
please.
yeah, of course.
Please, please.
No, go.
So so this is just a stateless statement that if I like consider, for instance, in the continuum, the Frankfurt theory, and I reduce it on the circle, I will have a coupling for the zero mode, which is something like lambda times the temperature, if I remember correctly. And can I just essentially derive this plot or like the idea of this plot directly from that, or is it a different thing? So it's just that. It's just the fact that the coupling run with the temperature, essentially, in one-dimensional less. Okay.
Yeah, exactly. That's right. And the nice thing about the screening mass is that this is sort of a standard observable that people look at finite temperature phenomenology. So when people look at, say, lattice QCD calculations, they look at these screening masses for different states like pions, kaons, and different states, and they look at how it evolves as a function of temperature. And then that's telling you something about, the phase structure of your theory. So it gives you a kind of observable to look at.
Right, of course.
Yeah.
Okay.
Yeah.
My question was instead probably easier in the sense that is this the first time that this discrepancy between lattice results and perturbative results has been observed?
Yes, as far in this model for sure, at finite temperature. So a lot of the studies
before this paper, like people just assume that lattice would have given the same result as perturbation theory. Okay.
Yeah. I mean, people
up to the observation, right?
Up to?
Like up to the observation that when you read, I mean, I think it was known, right? Again, you can just reduce it on the circle and you know that this will gonna happen. Probably that's the first time you observe it explicitly.
Yeah, exactly. People have known about these deviations for a long time in different contexts. It's just this is the direct, as I said, apples and apples, where you do your lattice perturbation theory with the same lattice parameters with the standard approach, and then you compare it to the lattice simulation with the same parameters. Yeah. So you see these deviations, and then the game or the goal is to try and figure out what's driving them. So what causes these deviations? So when you do these lattice perturbation theory predictions, you're doing a whole bunch of sums. That's the general idea, because all of your continuous integrals get turned into sums. This is what you have to compute for your spatial correlator. What you do is you compute the self-energy, which has different contributions, tadpole, your cactus diagram, your sunset at two loop, which can be written in terms of different nested sums. And then what you can do is you can start to look at, what's causing this behavior to be driven further and further away from the data. Long story short, what you can show is you can show that you get this behavior, this opposite screening mass behavior to what you'd expect, where you'd expect it to increase as a function of temperature. You can you can see that you get this behavior when this expression here, this is kind of a proxy for this behavior when this becomes negative. We'll see that this ends up being a competition between these two diagrams that drives this behavior, this strange opposite behavior to what you see on the lattice. So if you see here on the right-hand side, this is a plot of this function for different bare lattice parameters. And basically what you see is if you fix the coupling, as soon as you make the bare mass small enough, you end up inevitably in this regime where this is negative, where you get this strange behavior. So no matter where you are, you fix the coupling. If your bare mass is small enough, you will run into this issue. So what that is just telling you is it's telling you that it's an infrared problem. It's an infrared driven by the infrared dynamics of your theory. And it turns out that it's just driven by the infrared structure of your propagators that enter into the loops. So what you see is that if you go to sufficiently small bare mass, you're dominated by the zero modes. So the zero modes are just, as the name suggests, the zero momentum components of these sums. And what you can show is that the zero mode for this tadpole diagram and the cactus diagram, they scale with the bare mass in this way, 1 over m squared, 1 over m to the 4th. So it means for sufficiently small m0, this will outcompete this guy, and that drives this behavior. It drives the screening mass to go negative, and this is what causes these deviations away from the data. So this is essentially a long way of saying what was indicated before. It's the structure of the propagators that you use in your expansion that's causing these problems. It's causing your perturbative predictions to deviate from the lattice data, which is just what the NRT theorem is telling you. NRT theorem is telling you you can't have on-shell scattering states. So that means that using these standard propagators is not the correct way forward, because if you do that, you end up with a theory that has no interactions, a trivial S matrix. And in fact, this is the root of the problem. This is causing your deviations of your predictions from the lattice data, because you're using these propagators. So in a sense, you can think of these deviations are a kind of manifestation of this, the constraints that you get from this theorem. So basically what that means is it means that if you want to do perturbation theory consistently, if you take these constraints seriously and you see the lattice deviations, you need to use propagators that don't have purely real singularities. They need to have some complex part in their singularity structure. And of course, the million-dollar question in a way is, what form should these take? You could chuck in some propagator with an imaginary part, but how does that connect to the physics of your theory? And that's what I'll talk about in the next few slides. You know, what sorts of forms can these propagators take, and do they have the correct properties to form the basis of a perturbative expansion that avoids these issues, these deviations from the data, and also the known issues that we get here in standard perturbation theory. So to discuss this, that's where the notion of thermoparticles come in. So as I mentioned before at the start, hopefully if you take anything from this talk, it's this notion of thermoparticle, because this is quite a fundamental notion in finite temperature QFT. So what you find is that when you switch on a temperature, you immediately get changes, of course, in the structure of your QFT. So Lorentz invariance, of course, is no longer a symmetry of your theory because boost is broken, but you can retain rotational invariance. The spectrum of your theory no longer is positive, but is replaced by this KMS condition, the definition of equilibrium states, how you introduce temperature into the system. And as I mentioned briefly before, that actually causes you to have negative energy states in your theory. So clearly that violates this condition that you assume holds in vacuum. But what's nice is this condition, this field locality condition, or equivalently, it's just causality, how you impose causality in the theory. This is actually preserved at finite temperature. So this this holds independently of what state you put this in. So be it the vacuum state or thermal state, or even more exotic states that say have a finite chemical potential, say, this condition will still hold. And what I'll show is that actually this has really important implications for the spectral properties of your theory at finite temperature. So to discuss this, the important objects are spectral functions. So I'll be mentioning that a lot. And just as a sort of bookkeeping thing, I'll just define here exactly what I mean by a spectral function. So this is just simply the Fourier transform of the commutator of two fields. And what you can see, and what we'll see in the next couple of slides, is actually this constraint, the fact that this guy vanishes for space-like separation, has very important implications for the energy momentum structure of your spectral function. So when you're in the vacuum, the classic case is if you have a stable particle state, this would be a delta. This would show up as a delta in the spectral function. And then if you have a continuum onset, then this indicates you have multi-particle states. You can have some continuous structure like this. So what we want to try and figure out, because we want to know, what form should finite temperature propagators have in general, what are suitable forms to look for. We want to know what changes to this picture when we switch on the temperature, in particular when we relax these two conditions, but we keep this causality constraint. And this is what we find. So this is a representation that was derived in the sort of mid-early 90s by Jacques Bohr and Detlev Buchholz. And basically what this is just the finite temperature generalization of the textbook Gell-Mann-Low representation. So if we're in a vacuum system, your spectral function can always be written like this. Equivalent, you can write this in the form of a propagator as well. And this is the spectral density that, of course, tells you about the spectral excitations that you have in your theory. So, for example, if you have a stable particle state, this guy would just be your delta S minus m squared. And then this gives you the standard spectral function of a stable vacuum particle state. So what's important about this is this equation tells you that basically all of the temperature and the dynamical effects that get introduced from having non-vanishing temperature are all contained in this object here. This is the thermal spectral density. It's simply just the finite temperature generalization of this object. And what you see is that essentially by adding a temperature in the game, this gives you extra complications it gives you an additional parametric, different parametric dependence, an additional parametric dependence on this variable u. And essentially, as you can sort of see, if you kind of squint at this equation for long enough, the U dependence tells you how far off shell you can be. So it measures the kind of off shellness. So when U is non-vanishing, that means that you'll be off the mass shell. And the S dependence tells you about energy thresholds that you have in your theory, just like in the vacuum case. So this is a causal representation which is non-perturbative and is model independent. So this is true for this is true for scalar fields. So if you have two scalar fields, they can be fundamental or composite scalar fields, it doesn't matter. The spectral function in any theory can be written in this form. And this just follows from very basic principles. This basically causality and KMS condition and rotational invariance. So what's nice about this is that then this can be used in different contexts where you have scalar fields in the game. And we'll discuss that in the next few slides where we can apply this, for example, in QCD. So the game then becomes, if we want to understand the types of excitations that we can have in the spectral function, we need to classify the types of terms that can contribute to this thermal spectral density. And this is where the concept of thermoparticle comes about, that was introduced in these works. The idea is that basically if you have a stable particle state in vacuum, so that would mean that this rho has a delta S minus m squared, that at finite temperature, this manifests itself as a term that looks like this. So basically the delta in S is the same. Oops, so this is still a temperature independent mass. So this is the mass of your particle in vacuum, and all of the temperature effects get contained in this so-called damping factor. So now if you throw this into this equation, what you see is you see that you get a broadened spectral peak, and I'll show this on the next slide, when this guy has a non-trivial structure in U. So when you go to the zero temperature limit, this d of u becomes a delta, so that sets u equals to 0, and then you just recover back the standard representation of a particle. So in this sense, as the name suggests, this is the finite temperature generalization of a stable particle state. That's the idea. So as I said, as long as this damping factor is non-trivial, and as the name suggests, it basically characterizes the medium effects that your particle state experiences, the collisional broadening effects. As long as this is non-trivial, it means that your spectral peaks become broadened. So basically this here, that would be a standard delta peak of a stable massive particle state, this becomes broadened and has some associated width. And this comes from the parametric form of this damping factor. And what's very important about this is that the damping that particle states experience at finite temperature is different from theory to theory. So this is driven by the dynamics. And that's just basically because the medium that you have, the thermal medium, depends on the dynamics of the system that you're looking at. So the QED medium would be very different to a QCD medium or the medium in 5-4 theory. So now this becomes a dynamical question about how your particle states manifest themselves at finite temperature.
Can I ask you a question? So is this this thermoparticle essentially the particle with the reduced theory, or is it related to that? Or
particle of a reduced theory, of a dimensionally reduced theory, you mean?
Yeah, exactly.
Well, I don't think so. I think this is, I mean, maybe it can be connected. I mean, what you'd have to do is you'd have to look at this so this is obviously 3+1 dimensions, I should say, this representation. You'd have to look at this guy in 2+1 dimensions and then see, you know, if these guys are connected. So potentially, but it's not obvious because this representation changes when is strongly dependent on the dimension. So basically, if you go to say 2+1 or 1+1, the kernel here changes. Yeah. So what's nice about these thermoparticles is they have a threshold. So they're not some kind of bright Wigner peak, but they have a threshold. So that means that they're exactly 0 below the vacuum particle threshold. This is the vacuum particle mass, and they broaden to the right of this vacuum threshold. So the physics of that is basically that you need to kind of inject into the medium a minimal amount of energy in order to create these excitations with any probability. So basically you need to inject into the medium at least the rest mass of the particle in vacuum in order to create a thermoparticle excitation. So because you get this threshold structure, so this threshold structure just comes from this factorization. So when U and S are factorized in this form, when you throw this in here, you see that you actually get a threshold in the energy. It comes from this special form. What it also means, it means that the 2-point function has a factorized form. So the 2-point function of a thermoparticle degree of freedom can be written as the damping factor in position space multiplied by the 2-point function of a free particle of mass m. So that's where the term damping factor comes from, because it's really a multiplicative factor which reduces the kind of amplitude of detection of these particle states. The logic being that as the temperature increases, the mean free path of the particle decreases, and therefore the probability of detection of these particles also goes down. So what this means is it also means that these degrees of freedom actually dominate the large time behavior of your correlation functions, of your real-time correlation functions, which is of course interesting when we want to talk about scattering, because the scattering states are of course the large time states in your theory. So that strongly suggests that thermoparticles are a natural candidate for describing finite temperature scattering states. And I'll talk about that in the next couple of slides. Another thing that's nice about this structure, so this is noted here, this is a very nice review by Jacques Bohr, is that also because of this structure, the medium effects that are experienced are actually frame dependent, which makes sense because temperature is a frame dependent phenomenon. And it tells you that if you're in the rest frame relative to the medium, that you feel very few or very little temperature effects. And obviously, if you travel fast relative to the medium, the temperature effects that you experience are increased. So with this structure of how particles generalize to finite temperature, you kind of capture the sort of correct features that you'd expect on physical principles about how medium effects should affect the properties of particle states. And one thing that's very important actually is that as soon as you have this spectral representation, this actually tells you that your correlation functions have very different class of singularities, or can have a very different class of singularities to the singularities of in a vacuum theory. So generally in a vacuum theory, you'd have simple poles, particularly for lower lying states. What you can have here is you can have your lowest lying state actually having branch point singularities. So that's what you find in this specific case where you have an exponential damping factor. You see that your propagator has this form. If you choose different parameterizations, you can generate logarithmic propagators with logarithmic branch points. So this is something that's fundamentally different at finite temperature than it is in vacuum. The singularity structure of your propagators look very different. So I won't have time to talk about different applications of these, but I just want to mention that thermoparticles play a role in many different contexts. I'll focus on this for the remainder of the talk, but because the organizers mentioned this work about spontaneous symmetry breaking, I thought I'll sneak in a quick slide about this because this also relates to thermoparticles, this notion of spontaneous symmetry breaking at finite temperature. And also, I'll just mention this as well about the study of hadrons in QCD at high temperatures. This is something that we've looked at. So in short, basically thermoparticles seem to play a role in lots of different contexts in finite temperature QFT. So if we start with the QCD case, so in short, what this slide is saying is basically what we did is we tried to look for thermoparticle states in lattice QCD data. In particular, what we did is we looked at light pseudoscalar mesons and we asked the question, are these states consistent with being thermoparticles? So do they have this characteristic structure? Can we tell this from the lattice data? So what we did in these series of papers, first for pions and then for kaons and SS bar states, is we asked this question, are the lowest lying states in our spectral function consistent with having this thermoparticle form? So to do this kind of in short, what we do is we use the lattice data to extract the damping factor. And then once we have the damping factor, that gives us the full form of the spectral function, because once you know it has this thermoparticle form, you plug it in here, you get the full spectral function. And from this, you can make predictions of other correlated data. So what we do is we extract the damping factors from spatial correlated data, and then we use that to make predictions of temporal correlated data. And we'll play this same game again later in the perturbation theory, but this is a highly non-trivial cross-check because the spatial and temporal correlators depend on the spectral function in very different ways. And what we see basically in all of these channels is that we see that the pions and kaons, the low-lying mesons, still have a bound state-like structure, even at high temperatures, even above the so-called pseudo-critical temperature, above this crossover temperature that you have in QCD, we see that they still have a thermoparticle structure, and a thermoparticle structure is just a collisionally broadened hadron. So that means that these states still behave like they're bound states, even above the pseudo-critical temperature. Okay, so if you're interested for more details, we can discuss that at the end, but I just wanted to mention that thermoparticles make an appearance here in QCD for the QCD spectrum. And then, as I said before, I'll spend a little bit of time here just talking about thermoparticles in the context of Goldstone's theorem. So again, the same authors, Bro and Buchholz, they looked at asking the question of what happens to the Goldstone mode at finite temperature. So in essence, what they do is they use this extra information that you get basically from causality in order to infer what happens to the Goldstone mode as you increase temperature and you go above a critical temperature. And what they find is that they find that the Goldstone mode actually has the structure of a thermoparticle. And as you may guess, this is the structure of a massless thermoparticle, because in the vacuum state, of course, the Goldstone mode is an exactly massless particle state. So what we set out to do in these works is we set out to test this on the lattice. So basically what we do is we take a simple complex U1 scalar theory, and then we look at this on the lattice at different temperatures, and we see what happens to the Goldstone correlation function as we increase the temperature. And basically what we find is that the Goldstone mode has this massless thermoparticle structure everywhere, even above the critical temperature. The only difference is how the damping is of this mode. So what you find is that you find below the transition, you have weak damping, weak dissipation. So basically this is non-zero at large distances. And above the transition, we find that this damping factor is strongly dissipating. So basically this goes to zero at large distances. And what's interesting about this is that actually this determines the value of your order parameter. So with these, this is what's discussed in this work. So go here if you or these works if you're interested in the details. But essentially what this tells you is it tells you that the order parameter is switched on and off by the damping that the Goldstone mode experiences, the damping that the thermoparticle Goldstone mode experiences. So this damping is a constant in vacuum. So that means you have an exactly massless mode, and then you have this non-trivial difference. So what that means is that you can have a change of phase, but the change of phase is not driven by a difference in the degrees of freedom of your system, because the Goldstone mode is still there. The information is never lost. It's how the damping of that mode happens above and below the transition. That is actually what causes the order parameter to be non-vanishing or vanishing. And this, as I said before, this has the structure of a massless thermoparticle. So thermoparticles play an important role in physical theories like QCD, and also they seem, at least in these simple models, we've also looked at what happens when we have an external current as well, and then you get a crossover, but we also retain this structure basically. But now when you have an external current, you have a massive Goldstone mode in the vacuum, and we see that we basically get a damped massive thermoparticle mode. So yeah, basically thermoparticles are a feature of your QFT. They're motivated by this general spectral representation, and from lattice analyses in QCD and also in scalar theories, we find evidence for them as Goldstone modes in this case, and in the QCD case as the physical meson states. And work is ongoing also to look at, I should say these are obviously pseudoscalar states, but work is ongoing to generalize this also to higher spin states as well. So we can look at higher spin mesons, for example. And this is, sort of captures the physics, because it's just that sufficiently strong thermal effects just destroy the long range order here. And this is what leads to symmetry restoration in this phase. And therefore the order parameter is zero. Okay, so again, if there's questions or people interested in more details, I've got backup slides of this. So I'll just move on now to the last bit of the talk, which is just to finish off what we were mentioning before, which is perturbation theory at finite temperature. So as we said before, this NRT theorem puts these strong constraints, and now we see this in lattice data that indeed the standard approach doesn't agree with the predictions don't agree with the lattice data. So the suggestion is, why not use thermoparticles as the basis of perturbation theory at finite temperature? Because because of this structure here, they dominate the large time behavior. So they have the natural structure of scattering states in your theory. And that would mean that this Gell-Mann-Low relation is modified in this way. So now instead, your full correlation function is related in this way, but now your asymptotic fields are not your free fields, as they would be in the standard approach, but are actually these thermoparticle fields that create your asymptotic scattering states at finite temperature. And the big difference with these fields is that they know about the interactions in the system and they know about temperature in the system. So this is baked into the definition of these states because essentially this goes back to the NLT theorem. Temperature is everywhere in your system, also at large times. So that means the scattering states of your system also need to know about temperature and the dynamics of your system. So that's how this is encoded. So if you just follow exactly the same prescription as you would do in the vacuum theory or the standard formalism, you then just do an expansion of the exponential here, and this generates all of the diagrams. And interestingly, the diagrams have exactly the same topology as the standard approach, except now every time that you have a line, so if we were to create this diagram, for example, here, this propagator now would be replaced by a thermoparticle propagator, which doesn't have the standard 1 over p squared plus m squared form, but has a more complicated form that knows about the temperature of the system and also encodes the interactions of your system. So for example, something like this would be the basis of your perturbative expansion.
So can I ask, like,
Sure.
so what you're saying is that, like, in the computation, like the perturbative computation of a correlator like the one that you're showing at the moment,
Yeah.
like the dependence on the temperature is not only contained in the thermal state, but also each particle state needs to account for temperature.
Exactly. So before the formalism, it would just be contained in, say, the Matsubara sums that you have, but not in the propagators that enter those Matsubara sums. And now what it says it's in both. So it's in the basic propagators themselves, and then also you have the sums.
But is this like is this only a Lorentzian phenomenon or also a Euclidean phenomenon? Like
This is
would you
both.
have both?
So this is real time. So this expression is real time. So we do the lattice perturbation theory calculations in Euclidean time just for convenience, but this is a real time approach. So your real time
Yeah.
scattering states have this thermoparticle form. And that's kind of the powerful thing about these. If you have these types of degrees of freedom in your system, if they're there, you can actually prove. So that's proven in this paper here, that they actually dominate the correlation functions. So no matter what other excitations you have, you can have, say, low energy, purely thermal excitations below threshold. You can have above threshold stuff. All of those are subdominant compared to the thermoparticles. So these are kind of the long-lived excitations that live at large times.
Okay.
Yeah.
But
So then what
can I
you
ask
do,
you, like
yeah, sure.
concretely, like these thermal particles now are, I think, theory dependent, right? You said that
That's
they're
right.
theory
Yeah,
dependent.
exactly. Yeah.
So, like how you, like now you, I guess you want to construct like the perturbation theory around this, which I think is like a great idea. But since these are theory dependent,
How
don't
do
you
you
have
do
like
it?
to solve the theory?
Exactly.
To
So
solve the theory,
I'll
like
explain that. Yeah, I'll explain that. So
okay.
Exactly. So, and this is the quite amazing thing about these this work of Born-Buchholz is what they do is they actually define a consistency condition that the thermal asymptotic fields should satisfy. And this consistency condition you can actually prove uniquely fixes the form of the damping factors of your thermoparticle propagator states. So that means you can construct from the ground up a consistent perturbative expansion around these propagators. So they're fixed uniquely by the theory. So with general KMS states, they could be any old, have any old structure, but you can show with this consistency condition that they're uniquely fixed by the dynamics. This is in the backup slides, but I can just flash the backup slides here. So because if you're interested in the paper, this 2002 paper what they do is they basically say, okay, how do you define asymptotic states? So what they say is they say that the asymptotic fields should satisfy the equation of motion, the full one, but only at asymptotic times. So that means they're not the full interacting fields, of course. They're somewhere in between, and they're not the free fields as well as you'd have in the vacuum case. And what you can prove is that basically this non-perturbative condition fixes uniquely these damping factors and then the propagators. So that means that you can take, and in here they take 5/4 theory for negative and positive coupling, and you can derive the form of the propagator. So basically this consistency condition ends up becoming a differential equation that you can solve, and then this fixes uniquely the form of the propagators. So what that means is it means on a theory by theory basis, you have a way of defining perturbation theory, and the propagators that you use will be different in different theories, because that depends on the dynamics of the medium. So what
Sorry,
we do,
if I can follow up. So just to
yeah,
see
of
if I
course, yeah.
understand, like I can fix the structure of this thermopractical propagator for my favorite theory, even before computing any
Yes,
cut.
yes,
Okay.
exactly. And that's the big difference here. You set it from the outset with a non-perturbative condition. So before, what you do is you do a resummation, and you could resum, and then you could, write a sort of effective propagator. But here it's set from the start. So that means at tree level, these guys have a width that's determined by the coupling and the temperature and the mass of your theory, and that's fixed by the dynamical equation of your theory.
Okay. So
Yeah, and that's a non-perturbative condition. So basically, though that parametric form is fixed by infrared parameters in your theory, for example, like the mass of your physical states in your vacuum theory, for example.
okay.
And then that fixes the parametric form. So if you then have a general thermoparticle propagator, what you immediately see is that you see that when these get introduced, your, say, plus propagator in the real time, so this would be a real-time time-ordered propagator on the plus branch, both terms are broadened. So if we go all the way back to the start, where we had this propagator here, this is the standard one you use in real-time finite temperature perturbation theory, where you have a vacuum-like bit and a sort of on-shell piece. That turns into this expression here. So both bits get broadened. And what's nice about that is it means that if you do standard real-time perturbation theory at finite temperature, you encounter these pinch singularities because you get delta squareds, because when you square up these propagators, you get deltas, and then you have an issue, okay, we have to regularize it, and then we add all the diagrams and show that they cancel. But what this tells you is that they never appear, because the on-shell terms basically become broadened, and that's because your scattering states have a broadening because they know about the temperature from the outset. It also tells you that in massless theories, IR divergences are regularized. So when you have a broadening, you get a cutoff, an IR cutoff. And so that's very suggestive, because all of the problems, the deviations that you have here are all infrared driven. So that's because the basic propagator, the free field propagator that you use, diverges at zero momentum as the mass goes to zero. But as soon as you have these thermoparticle propagators, these divergences are never there, even for a massless theory. So that means you never need to do a resummation because the diagrams are always finite, even in the massless case. What you can also show is that the UV divergences that you get from doing this perturbation theory are also the same as the vacuum theory. And the reason for that is basically this damping that you introduce doesn't change the UV behavior. This is just about the IR behavior of your propagators. So then the question, as was mentioned before, okay, what form will they have? And as I mentioned there in the backup slides, you can in principle uniquely fix them from the dynamical equations. What we do here in this work is we just use a functional form that we choose. So we just choose an exponential damping factor. Gamma then, of course, measures the kind of width of this. So when gamma goes to 0, this becomes a constant, and then you recover a delta peak, which would be a standard, on-shell particle state. Or if you take this representation here, if you set gamma to 0, which is what should happen in the zero temperature limit, if you look hard enough, this turns into a delta. Basically, this becomes delta p squared minus m squared in that limit. So, and as you mentioned before, what happens is that broadening is already there at tree level. So at tree level, you already have a width that's there, a kind of non-perturbative width. And then on top of that, of course, you'll generate additional contributions from the dynamics that you have in the loops. So this is the picture. This is the one loop result. And this is the comparison with the standard approach at one loop. And there you get deltas or derivative of deltas. These are on shell. So clearly there's big differences between the one loop standard result and the thermoparticle perturbation theory. So what we wanted to do now is, okay, that's the formalism. So this is the idea. You have thermoparticles. They seem to be there in the lattice data in different models, and they seem to describe your scattering states in a consistent way. Can we look for this on the lattice? Can we do a lattice test again, just like we showed with the lattice test before, which showed that the standard approach breaks down? And so this is what we do. So what we do here is we fix the form of the damping factor from the correlated data. So you can do this. You can determine the functional form of your damping factor from the structure of your from the form of your correlated data. And what we find is that it is consistent with a purely exponential form. So that means that our Euclidean propagator have this structure. So this is just the Euclidean version of this guy here. This is the real-time version of that propagator with an exponential damping factor. And then what we do, so of course, when gamma is the width, when gamma goes to 0, you recover the standard Euclidean result. And of course, this then cuts off all of the infrared divergences that you had, because at p equals 0 and m equals 0, this is non-vanishing, whereas in the standard vacuum, in the standard case, this diverges at that point. So as I mentioned before, in a continuum theory, this is fixed uniquely by the theory, or at least there's a principle put forward of how you fix it based on the definition of your scattering states. But what we do is we actually fix the gamma from the lattice data itself. So what we do is we do a lattice perturbation theory prediction. So exactly the same business as what was done here. So all of these sums, but now just with thermoparticle propagators with this exact parameterization. And what we do is we do a prediction of the spatial correlated data at different gammas, and we tune the gamma such that we're as close as possible to the spatial correlated data. And then we repeat that procedure at different temperatures. And that tells us the value of gamma at the different values of temperature that we have in our system. And then what we do is we use that gamma to make a prediction of the temporal correlated data, a perturbative prediction. So we do a lattice perturbation theory prediction of the temporal correlator using the gammas that we got from the spatial correlator. And this is a pragmatic way of doing it because, this is not a continuum theory, of course. This has a lattice cutoff and so on. So this is a way of sort of pragmatically extracting that information from the lattice data. But as soon as we then do a prediction of the temporal, we are doing a genuine prediction because the spatial and the temporal correlators depend on the spectral function in very different ways. So you can have many different spectral functions that describe the same spatial, but give you very different temporal correlator predictions. Okay, so I've just said basically everything on this slide. So we extract these gammas at different lattice parameter values at different n tau, different couplings, different masses, and then we do a two-loop lattice perturbation theory prediction of the temporal correlator. And this is what we find. So we find that we get excellent agreement with the data. And what's nice about using this simple scalar model is we can have very, very high statistics. So the lattice errors in the temporal data are less than 1%. So we get extremely good agreement with the lattice data from our predictions. And if we compare it now to the standard case where gamma is 0, and that's where we use these propagators instead, you deviate drastically. So this is exactly the same as what I showed previously, but just with a different lattice parameter set. So you see that in this sort of vacuum case, So large temporal size, small temperatures, you agree well with the lattice data, but as soon as you squeeze the temporal size, you increase the temperature, you start to deviate more and more from the data until at this point you're very, very far. So the difference between standard perturbation theory and thermoparticle perturbation theory is this, is the difference between these two, these plots. So it seems to work. Now the question is, okay, how non-trivial is that? And what we tested, so I'll just mention this very quickly, is we tried a different parameterization for the propagator that also has a width, so it's broadened. So this is a Bright-Wigner. So this is not a thermoparticle which has a threshold below and then is non-vanishing above. This has a peak all the way down to 0 energy. And what you can do is you can play the same game. So you can basically do your predictions of the spatial with this propagator, tune the gamma, and then do the prediction of the temporal with the gammas that you extract. And what you see is you don't get a consistent agreement with the data. So you see that for example, here you undershoot and then overshoot. And we see this with all of the parameter sets that we've simulated. So we've done probably order 30 or 40 different parameter sets, and we see this same thing. We see that the thermoparticle prediction, specifically with this parameterization, describes the data consistently at all temperatures. The standard approach, of course, deviates very wildly, and using a Bright-Wigner parameterization, it doesn't match the data. So it shows that the predictions really do depend on the structure of the propagators. So the predictions that you make are actually sensitive to the structure of your scattering states. And so this would indicate that thermoparticles do indeed seem to be correctly or describing the perturbative expansion in the correct way. So just before the final slide, so what we can now do, once we get these gammas, we can look at their parametric dependence. So we can see how they change as a function of the coupling and the temperature and the mass. And that's what these plots are. So as we increase the temperature, aka we increase the inverse temporal size, we see that gamma increases with temperature, which is what you'd expect. So it means you have more interactions with the medium. The same is also true of the coupling, which is also what you'd expect. And with the mass, you see that the gamma decreases with the mass. And the logic there is that if you're heavier, you don't feel the medium effects as strongly. And therefore, the gamma, which is a measure of the interaction with the medium, that decreases. So this parametric behavior, which we extract from the lattice data, this is also consistent with the intuition for what we'd expect for this parameter. Okay, so there was a lot of stuff there. But the basic idea, of course, is that perturbation theory has known issues. And hopefully I've drawn your attention to this NRT theorem. It's a non-perturbative constraint that tells you that you can't do scattering at finite temperature with real states with a real dispersion relation. They need to have an imaginary part in their singularity structure. We've now seen numerical deviations of the standard approach, and we've tested this concept of thermoparticle perturbation theory because this notion of thermoparticles seems to be a natural candidate for describing these scattering states at finite temperature. And thermoparticles seem to be a ubiquitous feature of QFT at finite temperature. There seems to be evidence of these guys in many different contexts. And the predictions that we get with the lattice data now are very, very good agreement with the data. And just finally, here we just considered scalars. So this representation is just for scalars, and this is, of course, scalar perturbation theory, but this framework can also be generalized to arbitrary spin, and a task for the future as well, or ambitious task, is also to look at what happens when you go to non-vanishing density as well. What happens if you have systems with say, non-vanishing chemical potential? So in principle, these concepts can be generalized, and that's a work in progress. So thank you. Thanks.